So hello students, welcome back to my classes. So today I'll be discussing the topics on half-life period for a zero order reaction and for a first order reaction. So students, in your previous classes, we had derived the integrated rate expression for a zero order reaction, and we had also derived the integrated rate expression for a first order reaction. So today we shall move forward taking those integrated rate expression. We will be discussing about the concept of half-life period. Fine. So what is half-life? What is half-life? So this half-life, it is denoted normally by T half, or sometimes it is also written as T 50%. 50% means half. So first let us define this half-life period. So half-life period, it is defined as the time, for the reactant to reduce to half of its initial amount. Okay, so this is the definition of half-life period. So what is half-life period? Half-life period is defined as the time taken by the reactant to reduce to half of its initial amount. So the concept is really easy. Okay, so what does this mean? Say suppose we start with the initial concentration of a reactant. I'll write down this as A naught. Okay, I'll write down this as A naught. So this is the initial concentration of the reactant. This is the initial concentration of the reactant. Now we know we denote the initial concentration by A naught, R naught. Fine. So naught denotes the initial concentration. Now half-life concept. What is half-life concept? Say suppose now the concentration reduces to exactly half of this initial amount. The initial concentration was A naught. Now the concentration of the reactant reduces to exactly half of the initial amount. So half-life period is defined as the time, okay, where the concentration of the reactant reduces to half of the initial amount. So the time required for the reactant to reduce to half of its initial amount is defined as a half-life period. So this time taken for the reactant to reduce to half of its initial amount is defined as the half-life period. It's a simple concept. Say suppose after first half-life has passed, what is the amount of reactant left? A naught by 2. Suppose this is equal to 2 hours, say suppose. Fine. After 2 hours, what will be the concentration of reactant? A naught by 2. Say after another half-life has passed. That means after another 2 hours, what will be the concentration of reactant left then? It will be half of this. Half of this means half of A naught by 2. This is equal to 1 by 4 A naught by 2. So here again the concentration of reactant reduces to half of its initial amount. So time required for this is again known as a half-life period. Say another half-life has passed. So I can write this as 1 by 4. I can write this as 1 by 4. Say after another half-life has passed, say after another 2 hours, what will be the amount of reactant left? Again, it will be half of the initial amount, A naught by 4, half of this. Fine. So this will be 4 to the 8, this will be 8 times. So this is the concept of half-life period. So half-life period is defined as the time when the concentration of the reactant reduces to half of its initial amount. Now here, see, after first half-life is passed, what is the amount of reactant left? I can write down this as half A naught. After first half-life has passed, after second half-life has passed, what is the amount of reactant left? I can write this as half to the power 2 A naught. Okay, so this is the amount of reactant left after first half-life. This is the amount of reactant left after second half-life. And what is the amount of reactant left after third half-life? It will be half to the power 3 A naught. So after first half-life has passed, so let us generalize this now. Let us generalize this. Okay, let us generalize this. So I can say after first half-life, okay, what is the amount of reactant left? What is the amount of reactant left? So after first half-life has passed, what is the amount of reactant left? It is half to the power A naught. After second half-life has passed, what is the amount of reactant left? Half to the power 2 A naught. After third half-life has passed, what is the amount of reactant left? Half to the power 3 A naught. Fine. Now we can generalize this. So in this way, after 10 half-life has passed, what will be the amount of reactant left? Half to the power 10. After 20 half-life has passed, what will be the amount of reactant left? Half to the power 20. So after n half-life has passed, suppose after n half-lives has passed, what is the amount of reactant left? It will be half to the power n times here A naught. Okay, so from this generalization, we can easily calculate the amount of reactant left after certain half-life. It's easy. After 5 half-life has passed, what is the amount of reactant left? Half to the power 5 into initial concentration A naught. So this is the generalization. So here, okay, we have developed a concept about a half-life period. So half-life period again is the time when the concentration of reactant reduces to half of the initial amount. So in the previous classes, we have derived the integrated rate expression for a zero order reaction. So if you guys remember it, what was the integrated rate expression for a zero order reaction? It was T was equal to A naught minus A divided by K. This was the integrated rate expression for a zero order reaction. Fine. Now, when the time is equal to half-life, so half-life is defined as the time when the concentration of reactant becomes equal to half of the initial amount. Okay, so after half-life has passed, when the time is equal to half-life period, okay, or half-life period is defined as the time when the concentration of reactant becomes half of the initial amount. Now let us substitute this in this equation. So now instead of T, I'll be writing T half or T 50%, whatever, is equal to A naught. So as the time becomes equal to half-life, the concentration of reactant will become half of the initial amount like this. So divided by K. Fine. So therefore, for a zero order reaction, T half is equal to A naught by 2K. T half is equal to A naught by 2K. So 2 and K are constant. So we can say half-life period is directly proportional to the initial concentration of the reactant, is directly proportional to the initial concentration of the reactant for a zero order reaction. Fine. So a half-life period for a zero order reaction is directly proportional to the initial concentration of the reactant. Fine. Now, Again, another very important questions from your board exam level. So T half is directly proportional to A naught. So if I plot the half-life period versus your initial concentration of what? Obviously, initial concentration of reactant, like this. Okay, so I'll be getting a straight line again passing through the origin. Again, since the intercept is equal to 0 out here. So, as time changes, this thing will also change. Fine. So, I can again express this into y equals to mx plus c. So, in the y-axis, I have plotted T half. In the x-axis, I have plotted initial concentration. I get a straight line. Now, what will be the slope of this straight line? The slope, which is equal to tan theta, is equal to, what is the value of slope? Yes, 1 by 2k. The value of slope or tan theta is equal to 1 by 2k out here. So this is an important question as far as the board levels is concerned. So what have I done? I remember the integrated rate expression for a zero order reaction, okay, and applied the definition of half-life. So half-life is defined as the time when the concentration of the reactant becomes half of the initial amount. Then I have substituted. After substituting, I'll come at this equation where 2 and k are constant. That means T half is directly proportional to A naught. Since they are directly proportional, yes, I'll get a straight line. And yes, it's very obvious from the equation that the slope will be 1 by 2k. The intercept is equal to 0. Okay, so for a zero order reaction, as the initial concentration of the reactant increases, the half-life will also increase. For zero order reaction, as the initial concentration of the reactant increases, the half-life will also increase. Fine. Now, let us see this for a first order reaction. Let us see this for a first order reaction. So remember, half-life is written as T half, or it is also written as T 50%. Now I'm going to apply the same concept again out here. So for a first order reaction, for a first order reaction. Okay, so what was the integrated rate expression for a first order reaction? Yes, it was T was equal to 2.303 by K log A naught by A. So what is again A naught? A naught is the initial concentration of reactant. A is the concentration of reactant left after time t. So here also, okay, when T is equal to T half, so again half-life is defined as a time when the concentration of reactant becomes equal to half of the initial amount. Same definition. So let us substitute this in this equation. So instead of T, I will be writing T half. T half is equal to 2.303 by K log A naught. So instead of A, what will I write? A naught by 2. Fine. So A naught will get cancelled. So T half will be equal to 2.303 into log 2 divided by K. So remember students, it's better if you remember the value of log 2. So log 2 is equal to 0.3010. The value of log 2 is 0.3010. So let me substitute the value of log 2 out here. So T half is equal to 2.303 into 0.3010 divided by K. So on multiplying this, yes, what will I get? I'll get T half is equal to 0.693 divided by K. So how did I get this value of 0.693? By multiplying 2.303 with the value of log 2. So this is the expression of half-life period for a first order reaction. So let us closely look at this equation. So do we see any concentration term out here? No, we do not see any concentration term out. In the zero order reaction, yes, half-life was directly proportional to the initial concentration. Here we do not have any concentration term. So we can say that for a first order reaction, here half-life is independent of the initial concentration of reactants. Okay, for a first order reaction, the half-life period is independent of the initial concentration of reactants. And yes, this is a very important equation, and this is a very important question for your boards level. So whatever questions might come, show that or prove that for a first order reaction, half-life is independent of the initial concentration of reactants. So where do we start from? We start from here. We know that for first order reaction, this, then we'll put down the definition of half-life period. So here we see the half-life is independent of the initial concentration of the reactants. The half-life does not depend upon the concentration of the reactant. So what will be the nature of graph? So if I plot the half-life period versus your initial concentration of the reactant. So remember, initial concentration, either it is denoted by A naught or small a. So it is independent of the initial concentration, means I'll get a straight line parallel to the concentration axis like this. So this is the nature of graph, okay, for half-life versus initial concentration for a first order reaction. So why did we get this nature? Because we know the half-life is independent of the initial concentration. Here we do not have any concentration term. That means whatever initial concentration you take, okay, the half-life will not get affected. It is independent of the initial concentration. However, for a zero order reaction, half-life is directly proportional to the initial concentration of the reactant. So kindly practice the derivation of this half-life period for a first order and for a zero order reaction, and in the next class we will be discussing about the numericals related to zero order, first order and half-life period. Fine. So today I am going to conclude my class out here, and in order to get regular updates, yes, please subscribe to my channel so that you will get regular updates. Thank you.